And today we will basically try to connect the very formalism that we have in terms of biological variations. So the motivation is basically to have a version, to have a framework where we can link the variations that are plausible, the variations that become the basic bones of evolution. We would like to we would like to realize these variations in the framework of quantum mechanical laws. So this is our intuition. So the intuition here is basically to talk about the biological variations. Biological variations. We would like to connect them with the quantum mechanical predictions. We'll not be talking about any story here. We'll not be talking about any poetry here. We would like to have a formal thinking. We would like to understand it in a formal way. We would like to realize these biological variations, which are purely classical in nature, and try and see the connection. So here we are going to talk about the quantum or origins of biological variations. So this is something that we would like to understand, we would like to share, and we would like to have some understanding on. In fact, we don't understand things purely. Whatever we understand, we try to understand it beyond that. That is how human nature goes. So let's now talk about the description that we have. The description, from the description and then try to move into a formal understanding of the quantum mechanical connection to these biological variations. So what we are about to understand here is what we are about to realize here is not something metaphorical. So you will not connect it to some metaphorical state, and we are not trying to make an analogy of it, and at the same time we are not. It's not a pure imagination. It's pure. I may call it. It is the physical framework. It's the physical framework within which the biological systems work, and the biological variations they become possible. Okay, so this is the argument. So this is something that we want to understand. We want to realize, and we want to connect it to the basic quantum mechanical models, so that we may have some deeper understanding of these biological variations. So if we think about variations at the deepest level, where these biological variations come from, they come from those microscopic foundations. Those come from these particles, these atoms, electrons, protons. And biological variation in general, we usually treat this biological variation as a random process. And in realizing the random processes, we can say a random process acting on genes or a random process acting on molecules. But here we are trying to understand, we are trying to start our understanding of these variations within the framework of quantum laws. So variations does not begin at the level of biology. At the biological level, you have the variations, we may call them at macroscopic states. Here, the variations, it begins at the level of quantum physics. What am I trying to tell here is that I'm trying to put a thing across like the central premise of this whole process, what we call as biological variations, is basically a macroscopic expression. It is the macroscopic expression of quantum indeterminacy, of quantum mechanical laws. And these laws are constrained. These laws are constrained by the physical laws. And we already know about the laws that have constraints in realizing these quantum mechanical systems. And what we have these stabilized biological processes. The stabilized biological process is a result of that, these constraints, is a result of those constraints. This is not speculation. This is a consequence of how matter behaves. So this is our target. And before we talk about the biological fluctuations, we have quantum fluctuations at the atomic scale. Before we can talk about the biological variations, we have quantum mechanical variations at the atomic scale. Now, what is happening at the atomic scale? At the atomic scale, no system is ever completely still. No system is ever completely having zero energy. In its lowest state, the systems at microscopic level have an energy state, what we call as 0 point energy. So you have 0 point energy. It's coming from solving the harmonic oscillator problem. That is E is h bar omega, if I choose it as E naught. So we can express this thing formally as the 0 point energy. Your biological system has atoms and molecules. These atoms and molecules never come to rest. They have energy even if the temperature around them is 0. What this means is very simple. How can I translate this thing? It means atoms vibrate. Atoms vibrate and electrons fluctuate. Atoms are vibrating, electrons are fluctuating. Protons do not sit. They do not sit in fixed positions, even if your system is at absolute 0. Now, this motion that we are trying to describe here, this motion is not caused by the heat. See, any domain in classical framework, we try to explain it in the framework of thermal energy, heat. No, it's not the measurement error. No, it's not anything that you have environment that's making these disturbances to these atoms, electrons, protons, which are fluctuating, vibrating, oscillating. No connection, no heat. It's very fundamental. It's very fundamentally happening. The nature is doing all these things at these levels. So how can I extend this down to the biological consequence? So what is the biological consequence of this argument? Every biological molecule, every biological complex system exists. It exists in a constant state of this microscopic motion of the fundamental particles that these biological systems are made of. There are no fixed bonds between the atoms. The bonds between the atoms, they keep on varying. The angles between the atoms, they keep on varying. Zero temperature, no disturbance, no environmental distraction. Electronic distributions fluctuate. And these fluctuations, the fluctuations that are causing at a very, very fundamental level, that are originating from at that atomic level, at the level of electrons and protons, is like a continuous background of micro variability. So there is a background of micro variability, and variation is not injected into the biology. You don't inject variation in it. You're not supplying any energy to this biological system. It is inherited. It's inherited from the laws of science. It is inherited from the laws of physics. The biological variations that we have at the macroscopic level. Now let's try to differentiate the quantum indeterminacy versus the classical noise. So what classical noise here means is classical randomness. Classical randomness, it comes from our ignorance, basically. We treat it randomness. Quantum indeterminacy that we have talked about, it comes from the law. So if I go down to the very fundamental principle of quantum mechanics, the Heisenberg's uncertainty principle. This principle was given by what was his? It was Heisenberg, and there is a limitation, the limitation of measurement. But that limitation of measurement is not because of the error. It's a property of the nature itself. So in the classical world, what variations you choose, they seem to be ignorantly described. Now why this principle matters for biology? As I said, the uncertainty principle. Because of this principle, because of this fundamental postulate of the quantum mechanics, molecular positions are never exact. You don't have any exact position of a molecule. It's a distribution. It's filled with quantum mechanical probabilities. We are not talking about the randomness here. There are reaction pathways, and reaction pathways are never singular. You don't have a single atom doing its job. And outcomes are never fully, you cannot fully describe, you cannot fully determine the outcome of that distribution. So what happens here? Biological systems, they operate in a domain where certainty is impossible. You cannot predict things accurately as you can predict in classical framework. Protons tunnel. So you have tunneling of the protons. This is the key mechanism the quantum mechanical tunneling of the proton in our proteins, in DNA molecules. Now we move to a concrete mechanism here. We are trying to look for these variations, but these variations have a foundation of quantum mechanics. And here we are talking about the very quantum mechanical tunneling. What it means for a particle encountering a barrier, as many times described. You have a barrier, a particle encountering this barrier, and this barrier has higher energy than the energy of this particle. So classical physics tells us that this particle can never ever cross this barrier, because the energy of this particle is less than that of the barrier height. So there is zero probability that the particle will be on the other side. But quantum mechanics has a different story here, has a different valuable story here. Now, what quantum mechanics predicts here? Quantum mechanics predicts something else. You have this particle has less energy. It is impossible for this particle to penetrate this barrier. But quantum mechanics says the particle has a finite probability. It has a finite probability to be on the other side of the barrier. And this is true for these light particles. This is a reality of atoms. This is a reality of electrons, protons, and neutrons. It's a reality for the particles like protons. So how this probability works now? Now this probability is less. No doubt it's less. But this probability is never equal to zero. The particle has a finite probability to be on other side of this barrier, which is impossible to be penetrated by the classical particle. And can I connect it to the genetic materials now? Can I launch this understanding to the genetic materials? And what we have DNA, deoxyribose nucleic acid. And in this molecule, we have hydrogen bonds. And what hydrogen bonds? Hydrogen bonds contain protons. So you have a DNA molecule, you have protons in the DNA molecule. And these protons can tunnel, they can tunnel the barriers which are impossible for the classical particle to have. This tunneling can temporarily alter hydrogen bond configurations. You have a DNA molecule, and there are finite probabilities for these protons to cross the barriers which are impossible to be crossed classically. So you have a base pairing behavior. You have molecular recognition. And most such events, they vanish. Because your DNA is consistently having a variation. The particles are tunneling. It's not a fixed structure. Some persist long enough. They persist long enough to influence the replication. So life goes on with the replication, mutation. It goes without any intention. There seems to have no intention classically. There seems to have no direction classically. There only seems to have a probability. A probability keeps these mutations possible. The probabilities keep the formations possible. So the indeterminacy that we have, the indeterminacy that comes from Heisenberg's uncertainty principle, it becomes basically the basis Quantum mechanics does not predict the outcomes. What it predicts basically is, it predicts the distributions. It predicts the distribution of these electrons, protons. The state of a system evolves. It evolves as measurement yields the outcome probabilities. Once you measure it, you have an outcome, but before the outcome, there is a distribution. Now, this thing is not coming out of ignorance, as in case of the classical attitude that we have. This is how reality operates. This is how reality goes on and on. Now, let's go into the biological interpretation, because we are talking about this indeterminacy. Now, what is happening here is molecular systems. You have molecular systems, and these molecular systems explore. They explore multiple possible futures simultaneously. They do it, they explore it, they have it. And when interaction occurs to that quantum mechanical state, when interaction occurs to that quantum mechanical framework of particles in these biological systems, the act gives you one outcome. Only one outcome becomes actual. So variation is not selected in advance. It's not selected by the system. Come on, I'm coming. The rest of you will go off. It's basically resolved. It's resolved by the act of measurement on this system. So, to have more understanding, if we may state the things like, if we may argue that quantum mechanics has no goals, it does not basically favor complexity. It does not basically favor the survival. So if it does not favor the survival, it does not favor the life. It does not favor the diversity. What it does basically is it provides only allowed states. That is what is the argument. And that is basically what I'm hit again by again with. Because you also have forbidden states in the quantum mechanical framework. You have probability of transmission of this particle to a barrier, which is impossible. You have probabilistic transmission. And from these probabilistic things, the biological variation arises. Within this constrained probability space, where you have allowed and forbidden states, the states that you will have to be only allowed states. Now, let's have a formal statement. Let us say there is some omega. It represents all physical allowed molecular states. Suppose there is some omega. It represents all molecular states. Now, what does What does biological system sample state here? Well, it states that you have variations and variations occur. And these variations do not occur, they do not occur because outcomes are chosen, but because alternatives are permitted. This is how the classical argument can be for the biological systems. So what you have basically, you have an amplification from quantum mechanics to the biological systems. Your biological systems are macroscopic, and a quantum event alone beneath this biological system is not enough. Most of the fluctuations that exist, most of the fluctuations disappear. For variation to matter, for variation to exist, this amplification must exist. Your quantum mechanical amplification leads to the biological systems. So the pathway is, you start from quantum fluctuations. You start from quantum fluctuations. Then you move it to molecular persistence. So you have then molecules. And then it leads to cellular incorporation. It moves to cellular incorporation, and then you have a complete biological consequence. So what can I say here? I can say that the amplification is rare. But rarity does not mean insignificance. This is the argument. This is something that we are trying to understand. And how does this decoherence leads to this stabilization? Because you have decoherence, you have fluctuations at these states. You lead it to the stability through what's called as quantum superpositions. And quantum superpositions do not survive for a long time. Interactions with the environment causes decoherence, deviation from the coherence. And you have superposition of different kinds of disturbances. This leads us to, this converts possibilities, basically. This converts the possibilities into the classical outcomes. From these superpositions, you have these big classical outcomes. And biology does not prevent this. Biology basically, it filters the result. You have those stable states coming out of it. So what we have, you have a filtration. You have a filtration from randomness, because you begin from the randomness to a structured change. Now, I think that we are reaching to a core transition. What's that? That is, randomness exists at the quantum level. Okay? There is randomness. And structure appears at the biological level, macroscopic level. But we understand that is not that classical randomness that we have at quantum level. And between these two levels, between them, there exist some kind of constraints. There exist constraints, stabilization, and a repetition. And order does not oppose randomness. The order that we can expect in a periodic crystal, the order emerges from constrained randomness. You have the constrained randomness that leads to an order, that leads to symmetry, that leads to pure geometry. Now let's conclude it. I don't think what I'm coming on, but still I'm trying to understand it. So what I conclude is that biological variation is not purely random in nature. In the biological systems, you have variations, they are not random and not even purpose driven. There's not any kind of purpose that's driven out there. And they are not externally imposed. They are not externally generated. It is basically the natural outcome. It's a natural outcome of quantum indeterminacy. And this quantum indeterminacy is basically filtered. It's filtered by physical law. And what you have stabilized. This is basically stabilized by the biological processes. And this is how microscopic uncertainty that has everything to do with Heisenberg's uncertainty principle, it becomes macroscopic diversity. This can be the argument here. And this can be something that we realize, we understand. We try to understand. So to closing this learning, life does not begin with materialistic intention. It begins with a possibility. It begins with plausibility. It begins with that allowed state. And quantum mechanics supplies those allowed states. Quantum mechanics makes us realize these allowed states, the allowed possibilities. And what biology does, biology preserves a few out of them. And over time, over long duration of time, those preserved outcomes that are preserved by the biological system, they become the living world. They become the living world we observe. So I hope you like it. I hope you subscribe. And I hope you interact with this, a very